Hello everyone. Today we will discuss a very important topic, the calculation of the time period of oscillation for simple harmonic motion. Well, you see, we will discuss or restrict our topic till the spring mass system only for this method. Okay, however, it can be extended to other systems. Well, when we want to calculate the time period of oscillation for simple harmonic motion, what we do is that if it is linear simple harmonic motion, then we basically write down the net force and then mm, from net force we calculate the acceleration and express it in terms of this equation, and from this particular equation we take out the angular frequency and then the time period. If it is angular simple harmonic motion, then we will write down the torque and we equate the not net torque with that of the I multiplied by alpha. From there we take out the angular acceleration and make it equal to omega square multiplied by phi. Again, from there, we take out the omega and calculate the t. But you see, in both the cases, the analysis that we do or the approach that we follow are the vector approaches. Okay. The vector approaches in itself, sometimes it is difficult. We have to get the direction of the vectors right, and then only we will get the correct answer. Well, be it simple harmonic, angular simple harmonic motion or linear simple harmonic motion, the energy of the system always remains constant. It is because the simple harmonic motion involves the restoring force, which is conservative in nature. So we know that energy is the scalar quantity, and in case of simple harmonic motion, total energy remains constant. So if we can approach the problem from the energy point of view, definitely we will have a little less difficulty in the calculation. Sometimes this method is very, very effective when it comes to angular simple harmonic motion, especially in case of rolling motion. Okay, we will discuss that particular topic here. So let's start. We will first discuss how we can apply this particular method, and then we will take the example. Okay, to calculate the time period of oscillation using effective energy method, we will first follow the following steps. First, you see, whenever a system is given, we will first find out the mean position and then write down the condition for that. Once we do that, we will write down the total energy of the system. Total energy of the system at certain instant of displacement. If it is linear simple harmonic motion, we will write down the displacement at some linear distance x. If it is angular simple harmonic motion, we will write down the total energy at angle theta. Again, I am repeating, the total energy shall always remain constant because it is a conservative system. Therefore, the total energy with respect to time is also constant. Therefore, its differentiation will be equal to zero. And that is the crux of this particular method. Now, we will differentiate the total energy with respect to time, and then we will equate it with zero. And from there, we will calculate the acceleration. Now, if it is linear simple harmonic motion, this will be our equation. If it is angular simple harmonic motion, this will be our equation. In both the cases, we will get the omega. And once we get the omega, from there, we can calculate time period. How? Because for any periodic motion, we know that time period of oscillation is equal to 2 pi divided by omega. Okay. Let's use this equation to solve a very, very simple problem. This problem, we know how to solve it. Let's apply this particular method. Okay, here we are given a spring mass system and the surface is very smooth, and it is already mentioned that the system or the spring is at its relaxed length or the natural length. So what is the step one? To find out the equilibrium position, which is already given, x equal to 0. What is the next method? The next method is as follows. In the next method, we have to basically write down the total energy of the system at certain displacement. So we will imagine that the block is executing simple harmonic motion about this particular position. Here the potential energy is minimum, and here the potential energy is maximum. Okay, here the kinetic energy is again minimum. So we will write down the total energies somewhere at a certain distance so that we can get the instantaneous expression. Okay, so at this particular distance, we will write down the total energies. That's our step number 2. So total energy of the system will be the kinetic energy, which is half of mv square, plus energy stored in the system in the spring, which is half of kx square. This is the energy, kinetic energy of the particle. This is the energy stored in the spring. In the step number 3, we will differentiate this particular energy with respect to time, and we will make it equal to 0. So once we do that, we will get certain kind of equation, and let's see what we get. Here, remember this v and x both are instantaneous because we are writing it for certain instantaneous value. So this is half m ddt of v square plus half of k ddt of x square equal to 0. I will apply the chain rule. Half will be cancelled, so 2v dv dt plus k multiplied by 2x dx dt equal to 0. Okay, now this dv dt is nothing but the acceleration. This dx dt is nothing but the velocity. A bit of simplification. So we are getting ma equal to minus of k multiplied by x. So a will be equal to minus of k by mx. So what we have to do in the last step, in the step number 4, we will compare this equation with the standard linear simple harmonic motions equation, which is this one. So here we have k by m, here we have omega square. So once we compare both the equations, we are getting omega square equal to k by m. So omega will be equal to k divided by m. Okay. So what shall be the time period? The time period will be 2 pi by t equal to k by m. So the time period shall be equal to 2 pi m divided by k. So this is the example for a simple problem which can be solved using the force or force analysis very easily. However, we have applied the energy method. Sometime in the complex processes that we will see now, the vector method becomes very difficult and this energy method becomes very effective. Let's pick one of such questions. Look at this. This is not an ordinary translational motion. Here we have a disk, and the center of the disk is connected to a spring. I, 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 I urge all the students to pause the video for a moment, read the question properly, attempt the question by your own. Once you are done with your attempt, then only you see the solution. This will be the effective method of solving. Now, here what happens is that it is assumed that the spring is at its natural length, and this will be the mean position of the oscillation. Now, once this disk is given a little bit of displacement and then it is released, so what it will do back and forth. But while it is doing back and forth, it will roll also. Okay. So when we are writing the total energy, we have to make sure that the kinetic energy of this disk has two parts because its center of mass is translating and the whole disk is also rolling and it is pure rolling. So kinetic energy, let's say the center of mass's velocity is v. So this is half of mv squared. And since it is rolling, it will have rotational kinetic energy, which is half of moment of inertia multiplied by omega squared. Then we are writing the total energy of the system. The system also contains the spring whose energy will be the potential energy at a certain distance x. Well, now this disk is rotating about its centroid axis. Therefore, its moment of inertia about the centroid axis shall be equal to half of mr square. Okay. Since it is pure rolling, again, V will be equal to omega multiplied by R. So half mv square plus half mr square omega square plus half of kx square. Before we differentiate the energy, we are simplifying the expression. So 1 by 4, this R multiplied by omega, that will be V square, half of k square. I think we are done with the simplification. Now we will differentiate the whole expression into getting 0. Okay. So once we are differentiating the whole expression, ddt of, so this will be half m ddt of v square plus 1 by 4 ddt of v square plus half k ddt of x square. So this will be equal to m multiplied by 2 will be cancelled. So dv dt plus 1 by 4, 2, this 2 will be cancelled with 4. So this will be 2 m multiplied by again v dv dt plus 2 will be cancelled. This will be kx dx dt shall be equal to 0. Now m multiplied by v multiplied by a plus m multiplied by v half multiplied by a plus kx v equal to 0. Then v will be cancelled. So this will be 3 ma divided by 2 equal to minus of kx. So a shall be equal to 2k divided by 3m. And if I compare this, now the last step is as follows. I need to compare this with the standard equation, which is a equal to minus omega square x. So once we do that, so let me write it here. Let me write it here. Once we do that, omega square will be equal to 2k divided by 3m, right? So what will be t? T will be equal to 2 pi multiplied by 3m by 2k. Okay, that will be the answer. I hope this is clear. I think it is very much understood. Let's move to the next question. All right, look at this particular question. Here we have two springs. I urge all the students to pause the video for a moment, read the question, attempt the question by your own using the same method, and see the video, resume the video once you are done with your genuine attempt. Okay, I think all of you have attempted the question. Now let me proceed. Well, we have a cylinder. I consider this to be a solid cylinder whose moment of inertia will be equal to the moment of with that of the disk. Now, this particular disk or the solid cylinder is given a little push so that it starts rolling. Okay, and it is doing a pure rolling about its relaxed position, which is also the mean position. Now, you see, once it is doing the rolling, its center of mass will be displaced by a distance of, let's say, x. Let's say its center of mass is displaced by a distance of x. So what will be the velocity of the center of mass? Let's say the velocity of the center of mass is v. And we know that in case of pure rolling, the velocity of the rim or the surface is 2v. So if the center of mass has a displacement of x, this particular point, let's say P, will have a displacement of 2x. Therefore, this particular spring shall be compressed by a distance of 2x, and this spring will be extended by a distance of 2x. Now I will write down the total energy. So total energy will be as follows: half of mv square. Let me first kinetic energy plus potential energy. In the kinetic energy, first we will write down the translational kinetic energy of the disk. Then we will write down the rotational kinetic energy of the disk. Now, when it comes to potential energy, there are two springs. So we will have to write down the potential energy for both the springs. So that will be equal to, for one spring, it will be half of k, and the displacement here is 2x. Then we have two springs. I think this is what the total energy will look like. Then half of mv square. Since it is cylinder, the moment of inertia will be half of mr square by 2. Okay. After that, 4x square. Okay. Half mv square plus 1 by 4 mv square plus 4kx square. That's the total energy. Now we will go to differentiate this particular expression. So let me differentiate this with respect to time. So what we are getting is, I think better we should add both the kinetic energy so that it becomes easier for us. Okay. So what will be this? This is 4, 2 plus, so it's 3 mv square plus 4kx square. Okay. So dE dt equals 0. So let me differentiate the whole expression: 3 by 4 mv square plus 4kx square. Okay. I think the writing is understood. Kindly spare me if you fail to comprehend any uh, word. Okay. 4k ddx of x square equal to 0. So this is 1 by 4 m 2v dv dt plus 4k 2x dx dt equal to 0. This will be 3 by 2 m v a 8k x v equal to 0. So v cancel. So 3 by 2 ma shall be equal to minus of 8kx. So after that, we will write down the expression for the acceleration, which will be equal to minus of 16k divided by 3m into x. Now that's our equation for the acceleration. What we will do now, we will compare this equation with the standard equation. Where shall I write? Let me write it here. So a will be equal to omega square x, which is the standard equation. Now I will compare this term with that of the omega square. So omega square shall be equal to 16k divided by 3m, right? So time period will be equal to 2 pi square root of 3m by 16k. Okay. So that will be the answer. I hope this is very much clear. Okay. So I request you to do this particular question and this particular question. And I want you to write down the answer for this particular question and check whether the effective energy method can be applied here or not. Okay, please comment. And if you want, I can make another video of this. This question is taken from old AITS, and it is also there in an Olympiad. Okay, so you try at your own if required. Please comment. I will make a video. Thank you.